Welcome back. In this video, we are going to talk about polytropic processes and ideal gas equations combined together. So first question, what is polytropic processes? Let's start from the most fundamental equation of work. It's W equal to integral P dV from V1 to V2. This is the most fundamental equation we can use to calculate work. And then we introduced another equation, it's called P times V with the index of n is equal to constant. And any process that follows this equation is called polytropic process. Okay, so what is a polytropic process? As long as the processes follow this equation, which is P times V with the index of n equal to constant, then this process is called polytropic. And what is n? N is a material property. N depends on the gas. It depends on what kind of gas you have. And then we combined those two equations together. We solved this integral. It's W equal to, the short version is P2V2 minus P1V1 divided by 1 minus n. That's the equation we derived. That's the case when n is not equal to 1. Okay, so this is the equation we derived before. And today, in addition to this equation, we're gonna introduce how the ideal gas equation will change what we already have. Okay, so now let's recall. For ideal gas equation, we have PV equal to mRT. So now we can plug in this equation back to the equation above. We can rewrite PV with mRT. So this equation will become W equal to, okay, so first one P2V2, it can be rewritten to mRT2 minus the second one P1V1, which can be rewritten to mRT1, and then divided by the denominator, which is 1 minus n. So finally, our solution is W is equal to, we can take mR out of the two terms, and it becomes T2 minus T1 divided by 1 minus n. And again, n is not equal to 1. You can use this equation if it is ideal gas. It applies to polytropic and ideal gas. Okay, and there's no need for us to add a subscript to mass m or r gas constant because they're constant, they don't change. Okay, so this is the equation we have.